Hello everyone, today we're going to look at some of the most common probability distributions: binomial, geometric, negative binomial, and Poisson, and understand how they're actually connected. When I first learned these, I remember feeling completely overwhelmed. They felt like separate formulas that I just had to memorize. But over time, I realized they are connected in a very logical way. And once you see that structure, everything becomes much simpler. Now, firstly, what are discrete probability distributions and why are they important? Discrete probability distributions describe the likelihood of each outcome for a random variable. These outcomes are distinct and countable. For example, heads or tails, rolling a dice, or the number of customers entering a store. Discrete distributions are different from another main group of distributions called continuous probability distributions. Continuous distributions can consider any outcome along a number line. For example, looking at the distribution of heights in a year group. There are many different types of discrete probability distributions, which serve different purposes and allow someone to understand different information from the set of data. Almost every common discrete probability distribution is just a different way of repeating or extending one simple idea. The Bernoulli trial. The Bernoulli trial is an experiment where there are only two possible outcomes: success or failure. These could be heads or tails, win or lose, defective or non-defective. Surprisingly, many complex systems can often be decomposed into many simple yes or no decisions. For example, human life is continuous and uncertain. But when actuaries model mortality, they often look at small time intervals and ask, did the person die during this period, yes or no? By stacking many tiny yes or no intervals over time, they can model survival curves and life expectancy. A single Bernoulli trial follows a Bernoulli distribution, which shows the probability of success for only one trial, for example, flipping a coin once. The Bernoulli trial only has one parameter, which is probability of success. Now, you may wonder how we could use the Bernoulli trials and the Bernoulli distributions to create other distributions which are more complex. The simplest way to extend a Bernoulli trial is to repeat it. Instead of performing the experiment just once, we perform the same independent experiment multiple times, each with the same probability of success. When we add up the number of successes across these independent trials, we obtain the binomial distribution. The binomial distribution models the number of successes in a fixed number of independent trials. Its two parameters are the number of trials and the probability of success. This means that if you want to calculate the probability of getting exactly 2 wins, for example 2 heads, in 10 coin flips, you can use the binomial distribution. While coin flips are simple, the binomial distribution becomes powerful when modeling real-world systems. For example, if an insurer knows that each policyholder has a 2% probability of filing a claim in a year, the binomial distribution can model the number of claims among a portfolio of 200 independent policyholders. The binomial distribution tells you how likely it is to achieve a certain number of successes within a fixed number of trials. But what if your goal is reversed? What if you want to know how many trials it will take to reach a specific number of successes? This is where negative binomial distributions come into play. Instead of keeping the number of trials fixed, we are now keeping the number of successes fixed. Therefore, the two parameters for the negative binomial distribution is the number of successes and the probability of success. It is a distribution that models how long we must wait to achieve a fixed number of successes. A real-life example could be an insurer asking, how many months will pass before we experience 3 weather-related catastrophe claims? Something interesting is that if you set the number of successes to 1, you would get a geometric probability distribution. I've noticed that the geometric distribution is often introduced before the negative binomial distribution. However, I personally find it more intuitive to understand the negative binomial first, since the geometric distribution then appears naturally as a special case when the required number of successes is 1. Geometric distribution allows you to find how long it takes until the first success. We are often interested in the first success because it represents the moment a process changes state. The first claim, the first sale, the first failure. The geometric distribution models this critical waiting time. The last distribution we will look at is Poisson distribution. Compared to the other distributions, Poisson is a little different as we are looking at what happens during a time frame, instead of a fixed number of trials or successes. Even though the Poisson distribution has a different form, it is not unrelated to the binomial. In fact, it arises naturally from the binomial distribution when we consider a large number of trials with a very small probability of success, while keeping the average number of successes fixed. So, we can find Poisson by finding the limit of a binomial distribution. The Poisson distribution models events that occur randomly over a fixed period of time. Although we often describe these as rare events, this does not mean that they are unusual in everyday life. Instead, it means that within a very small time interval, the probability of the event occurring is very small, and the chance of more than one event occurring in that tiny interval is practically zero. For example, car accidents may happen daily in a city, but the probability of an accident occurring in any given second is extremely small. When we divide time into such small intervals, the Poisson distribution naturally arises. In the Poisson framework, we no longer talk about probability of success per trial because there are no fixed trials. Instead, we describe the process using a rate, the average number of events occurring per unit of time. And although we've derived the Poisson distribution from the binomial perspective today, it can also be developed from a continuous time framework known as the Poisson process. Stepping back, we began by fixing trials, then fixed successes, and finally fixed time. Although these distributions answer different questions, they all rely on the same underlying idea: independent events. That shared foundation is what allows us to see them not as separate formulas but as connected pieces of a bigger structure.